You know, every smartphone, every computer, pretty much every piece of modern tech works because we can control the flow of electricity with absolutely incredible precision. But how? How do we actually do that? Well, today we're going to dive deep inside the silicon chip to understand one single crucial concept that makes it all possible, the Fermi level. So that's the big question, right? How do we pull this off? And we're not just talking about flipping a switch on or off. We're talking about building mind-bogglingly complex logic gates with millions of transistors on something smaller than your fingernail. To even begin to answer this, we need to see the world from an electron's point of view. To get our heads around this, the first thing to know is that electrons inside a solid can't just have any random amount of energy they want. Nope, they're kind of picky. They can only exist at specific energy levels, which are grouped together in what we call bands. You can think of it like a ladder, or maybe even better, floors in a building. Okay, let's break down that building analogy. The valence band, that's like the ground floor. It's where electrons are comfy, bound to their atoms, pretty much stuck in place. Then you have the conduction band. That's the top floor. If an electron can get enough energy to make it up there, it's totally free to zip around and carry a current. And the space in between? Well, that's the band gap. It's the forbidden zone, and it's basically the price of admission, the energy an electron has to pay to jump from the ground floor to the top. So we've got our building with its allowed floors. But where are the electrons actually hanging out? Are the floors packed? Are they empty? To answer that, we have to introduce the real star of our show, the Fermi level. This concept is the key that unlocks, well, pretty much everything. Now, the Fermi level isn't a physical place an electron can actually be. It's more of a statistical tool, a line in the sand. What it tells us is the probability of finding an electron at a specific energy level. Think of it this way. Below this line, states are almost certainly full of electrons. Above it, they're almost certainly empty. It's the probabilistic tipping point. To really visualize this, imagine all the electrons in a material as this huge, vast sea. At the coldest possible temperature, we're talking absolute zero. This sea is perfectly calm, totally still. The surface of that sea? That's the Fermi level. Every single energy state below the surface is filled with an electron, and every state above it is completely empty. But what happens when we add some heat? Well, that sea is no longer calm, is it? Temperature creates waves, and that sharp dividing line gets a little fuzzy. Some electrons get splashed up with enough energy to jump clear over the band gap and into the conduction band. Once they're there, they can conduct electricity. And when they make that jump, they leave behind an empty spot in the valence band, which we just call the hole. So in a perfectly pure semiconductor, what we call an intrinsic semiconductor, for every electron that gets splashed up, a hole is left behind. It's all perfectly balanced. And because of this perfect symmetry, our C level, the Fermi level, sits smack dab in the middle of the band gap. This is our neutral, perfectly balanced starting point. Okay, a pure semiconductor is balanced and all, but honestly, it's not very useful for building computers. To get real control, we have to intentionally break that balance. We need to hack the silicon, and the way we do that is through a process called doping. Let's walk through how this hack works. You start with the perfect crystal of silicon, where every atom is neatly bonded to four neighbors. Then, we sneak in an impurity, an atom like phosphorus, which actually has 5 electrons to share. 4 of those electrons form bonds just like silicon would, but that 5th electron, it's just kind of left over. It's an extra, a donor electron that's only loosely held, which makes it incredibly easy to knock into the conduction band. So how does this change our electron C? Well, by adding all these donor electrons, what we call N-type doping, we've basically raised the C level. The Fermi level moves up, getting much closer to the conduction band, and that makes it way easier for the material to conduct electricity. And you can bet we can do the exact opposite. With P-type doping, we add atoms with only 3 valence electrons. This creates an excess of holes, which effectively lowers the Fermi level, bringing it closer to the valence band. This ability to shift the Fermi level up or down on command is the absolute foundation of all modern electronics. So a little bit of doping gives us control. That's great. But what happens if we really push it? What if we just cram the semiconductor with a massive amount of impurities? Well, as you might guess, things start to get really weird, and we start to see some fascinating quantum effects pop up. This is known as the Moss-Bernstein effect. Basically, we've added so many extra electrons that our C level, the Fermi level, has risen so high that it's now inside the conduction band itself. The whole bottom of the conduction band is completely flooded with electrons. And because of a fundamental rule in quantum mechanics, the Pauli exclusion principle, which says no two electrons can be in the exact same state, any new electron that wants to get excited has to find an empty spot way, way up above the Fermi level. This makes the energy jump, the apparent band gap, look much, much bigger. And that's not all. Shoving all these foreign atoms into the crystal lattice kind of messes up its perfect structure. This distortion creates a whole mess of new, localized energy states. And these states blur what were once super sharp edges of the valence and conduction bands, creating what are known as band tails that just sort of smear into the forbidden gap. So we figured out how to control the semiconductor itself. Fantastic. But for any device to actually work, you have to get electricity in and out. That means connecting it to a metal contact. And this interface, this tiny junction where metal meets semiconductor, has been a massive engineering headache for decades. Okay, here's the theory versus reality. The ideal model, the textbook version, says that the energy barrier an electron has to get over to go from the metal to the semiconductor should be simple to control. You just pick a different metal, you get a different barrier. Easy. But in the real world, it just doesn't work that way. The Fermi level at that interface gets stuck or pinned in one spot, and it just doesn't want to move. This plot shows the problem perfectly. That straight diagonal line, that's the dream. That's the theory. As you change the properties of the metal, the energy barrier should change right along with it. But now, look at the actual data points for real metals. They're almost flat. It doesn't matter what metal you use, the barrier barely budges. The Fermi level is pinned, and this has been a huge limitation on our ability to design better and better electronic devices. So how do you solve a problem that's been bugging engineers for over 50 years? The answer, it turns out, is to stop thinking in 3 dimensions and start thinking flat. The solution lies in the incredible world of 2D materials. The breakthrough is to make a junction not with strong, messy chemical bonds, but with these incredibly weak forces called van der Waals forces. Imagine just gently placing one atomically thin sheet of metal on top of an atomically thin sheet of a semiconductor. This super weak interaction doesn't create all those disruptive states at the interface that cause pinning in the first place. The Fermi level is finally free. And this just blows the doors wide open. What you're looking at here is basically a design menu for next-generation electronics. On the left, you've got all these different 2D semiconductors and their energy levels. On the right, a whole family of 2D metals and their energy levels. For the first time, engineers can literally just pick and choose the right combination to create the exact energy barrier they need for any given application. It's a game changer. And here is the proof that it really works. By carefully picking a 2D metal and pairing it with the right 2D semiconductor, scientists have created a junction where the barrier for holes to get into the semiconductor is effectively 0. This is a perfect ohmic contact, which means there's pretty much no resistance at the junction. This is the holy grail for making high-performance transistors. And you know what? Solving Fermi-level pinning is just the beginning. These 2D material junctions are also atomically flat, which means perfect interfaces. They're transparent, they're flexible, opening the door for totally new kinds of devices we've only dreamed of. You can even use an electric field to actively tune the energy barriers on the fly. It's a whole new paradigm. Which brings us to our final question. We've journeyed from understanding the probabilistic nature of the Fermi level all the way to using that knowledge to build perfect atomic scale junctions. We have gained an incredible, unprecedented level of control. So, are we on the cusp of a revolution? Are we about to leave the age of silicon for a new era of flexible, transparent, and ultra-efficient flat electronics? Only time will tell, but it's going to be really exciting to watch.